everybody and welcome back to another brainstorm. Today we're going to be talking about waves. We're going to mention 3 points about waves in this video. First of all, we're going to mention the two different types of waves. We have transverse and longitudinal waves. Then we're going to talk about the properties of waves, and then we're going to finish by talking about this wave equation. So let's get into it. So let's just mention what is a wave in general. So the main definition is that a wave is a transfer of energy from one place to another, and these waves often pass through a medium. So what is the medium? It's a material that the wave passes through. This could be solid, liquid, and gas. Most waves will pass through a medium, but not always. We'll come on to that later. And the most important thing to know about the medium is that it is the wave that travels and not the medium. And all of our waves are one of two types. We either have a transverse wave or a longitudinal wave. So here we have two examples of waves. First of all, we have water rippling on the surface, and this is an example of a transverse wave. Remember that we said that the wave is a transfer of energy, and in this case, the water wave is transferring kinetic energy. Our medium in this case is going to be the water, so we have a liquid medium, and the most important thing to know is that it is the wave on the surface that's moving and not the water itself. Our second example is sound waves, so the sound that we hear. This is an example of a longitudinal wave, and the energy that's transferred here is sound energy. Our medium is the air around us, so we have a gaseous medium, and the most important thing to note is that it is the sound waves that are moving and not the air. Alright, so let's get on to our first type of wave, and that is a transverse wave. So the most characteristic thing that you'll see about these waves is that the wave moves up and down, like what you'd imagine a wave to be. And this up and down movement of the transverse wave is called an oscillation. Okay, you remember that we said that all waves transfer energy from one point to another, and we can mark that direction of energy transfer here. You can see that the oscillations of this wave go up and down compared to this direction of energy transfer. Now, two characteristic features of the transverse wave is the crest and the trough. So the crest is the uppermost point of the wave, and the trough is the lowermost point of the wave. And the most characteristic feature of these transverse waves is that our oscillations are perpendicular to the direction of energy transfer. So perpendicular means they move at a 90-degree angle, so you'll see it goes 90 degree here, 90 degree here. Another thing is that transverse waves do not always require a medium. The most notable example is our electromagnetic waves. A couple of examples of transverse waves could be vibrations on a string, for example, ripples like we saw on the water surface, electromagnetic waves, and seismic S waves. Okay, so we have our second type of wave, which is the longitudinal wave. Now, the first thing that you'll notice is that this guy doesn't really look like the up and down transverse waves. It looks a little bit more like a barcode. The most important thing that we need to know about longitudinal waves is that we have particles moving from side to side. Why is this? It's because all longitudinal waves require a medium. It's not like our transverse waves, like the EM waves that we talked about, where they don't need a medium. All longitudinal waves have to have a medium, i.e. a material to pass through. So once again, we can mark our direction of energy transfer, but this time our oscillations are parallel to the direction of the energy transfer. So our particles will be moving from side to side here, and these two lines are parallel. Two characteristic features of longitudinal waves are compressions and rarefactions. So compression is this region here. You'll see the lines are very, very close to one another, and this is because the particles are very close to one another, so the material is of higher density. And then we have the opposite to a compression, if you will, and that's called rarefaction. That's this section here, where you'll see the lines are quite spaced out. This is because particles are spaced out and the material is of lower density. Okay, so for the second part of this video, we're going to be talking about the properties of waves, and for that we will be naming and explaining each of the key features of both of our transverse and longitudinal waves. We have 5 key features that we'll mention in this video. That is the amplitude, wavelength, frequency, period, and the wave speed. So let's get into it. Okay, so the first key feature of the wave that we have is the amplitude. Now, the amplitude of a wave is the maximum displacement from an undisturbed point. So if we look at this diagram here, our undisturbed point is going to be in the middle, where the wave goes up and down essentially equal amounts, okay? So the maximum displacement is going to be the crest here, so because that's the furthest distance from this undisturbed point, and this distance here is our amplitude. It could also be this trough as well, because that's also the furthest distance away, and that could be the amplitude as well. Now we usually express amplitude as A, and it's measured in nanometers, which is a very, very small distance. Okay, so then we have the wavelength of a wave, and this is the distance from a point on the wave to an identical point that's adjacent to it. So we take a look at this transverse wave here. We could take this bottom point called the trough, find the next identical adjacent point. So that's going to be the next trough along, and the distance between these two is our wavelength. Equally, we could take the two crests at the top, distance between them would be our wavelength, or any point on the wave, so it could be the middle, but all we have to do is find the next identical point. So it would be the middle of the next wave, and that would be our wavelength there. We can do exactly the same for this longitudinal wave. We just have to find two identical points that are next to one another. So we could go for the end of this compression here to the end of the next compression there, and that length there would be our wavelength. Or it could even be the middle of this rarefaction and the middle of the previous rarefaction, and that would be the wavelength there. You'll notice that I'm using this strange symbol here to show the wavelength, and that is the Greek letter lambda. It looks a bit like an upside down Y, but that's the symbol we use to denote our wavelength. And our wavelength is always measured in meters. Alright, so then we have the frequency of a wave. And the frequency is the number of waves that pass a certain point every single second. Our frequency is measured in a unit called hertz, Hz, and 1 hertz is one wave passing a given point per second. So for example, if we said that this is the wave that passes a given point in 1 second, we can count how many waves we have. So if we start off with this crest here, we go to the next crest and that shows us 1 wave, go to the next crest, that shows us 2 waves, and we have half a wave here because it goes down to the trough. So we have 2.5 waves passing per second. We know that 1 hertz is 1 wave passing per second, so we can say that our frequency for this wave here is 2.5 hertz. Okay, so the next feature of the wave that we need to know is the wave's period. The period of the wave is the time taken for the wave to pass a given point, and it is measured in seconds. So this is our main equation that we need to know for wave period, and it's that wave period is 1 over the frequency of the wave. Pretty simple equation, we just need to be able to apply it. Usually for these equations we like to make a triangle, like so. Okay, so we've got a question here. What is the frequency of a wave with a period of 2 seconds? Okay, so we can see from this triangle that frequency is 1 over time period. Our time period is 2, so it's 1 over 2. So our frequency is going to be 0.5 or a half hertz. Okay, so then we have the wave speed, and as the name suggests, this is the speed that a wave passes through a medium, i.e. how fast does this wave travel through a material. And because of that, it is the speed at which energy is transferred by the wave, because you'll remember that that is the main role of the wave. Like most speeds in physics, wave speed is measured in meters per second, and this is the main equation we're going to look at for wave speed. And that is that the wave's period is equal to the wavelength over the velocity. Velocity is just a way of saying wave speed, or T is lambda over V. So we can write T, lambda, V, and we have our equations triangle. Let's just try this example at the bottom. What is the wavelength of a wave which travels at 10 meters per second and has the period 20 seconds? So we've been asked to find lambda, we've been given V, and we've been given T. We can see here that lambda is T times V, so we'll write that out. Lambda is TV, so T20 times V10 is 200 meters. Okay, remember our wavelength is measured in meters. Okay, so now we've talked about the different wave properties, we can unify some of these in this wave equation here, and this is what the wave equation is. It is that the wave's speed, or the velocity measured in meters per second, is equal to the wave's frequency measured in hertz times the wavelength measured in meters. So we can create this equation triangle to use in our various questions, because we know that V is F times lambda, so just like so. We can manipulate that to answer a wide variety of questions. We've got 2 examples that we're going to work through here. So first of all, it is what is the wavelength of a sound wave with a frequency of 500 Hz and a speed of 330 meters per second. So we've been asked to find lambda, we've been given F frequency, and we've been given V speed here. Okay, so we can see from here that lambda is equal to v over f. So it is equal to a speed of 330 over a frequency of 500. So therefore we know that lambda is 0.66, and you remember our wavelength is measured in meters, so 0.66 meters or 66 centimeters. Second example, a sound wave passes through a solid wall. It has a wavelength of 0.25 meters and travels at 400 meters per second. What is the frequency? So here we've been given lambda, we've also been given v, and we've been asked to find f. So we can see here that f is equal to v over lambda. So that is equal to our speed, 400 meters per second, over our wavelength, 0.25 meters. So therefore we know that our frequency is 1600 hertz. So you'll see that this wave equation here is really useful. It allows us to answer a wide variety of questions. And with that, I'd just like to say thank you guys all for watching. Make sure you hit like and subscribe if you want to see more videos like this, and I'll see you guys soon.